In example 6 here, we want to look at how fast is an angle changing. That's going to be a derivative at 200 feet down the shore if a boat is traveling at 150 feet per second and 100 feet from the shore. So here's our picture, and this idea for this problem comes from the Kankakee Regatta, where they have these incredibly fast boat races every year. And I was trying to take pictures one year, and the boats were, kind of screaming down the shore, and I was panning my camera. So I kind of had my camera right here, had an SLR, a good sized lens on it, and these power boats were just speeding down the shore, and I was trying to get the power boat and sort of blur the background to make it accentuate how fast they were going. So now, just to give you an idea of what these boat races look like, let me show you a couple of short clips here. So this first one is actually the panning angle, but then also shows a wreck of the boat. It just kind of caught too much air and boom, it was gone. And then to kind of get a little bit more feel for what's going on here, let's put you inside the boat. So this was a helmet cam that the driver was wearing here. These things go really fast. And they're just doing an oval loop on the Kankakee River. So that'll kind of give you a flavor for what we're looking at here. So you got this power boat out there. It's traveling 150 feet per second. I think that's approximately 100 miles an hour. It's 100 feet from shore, so this is fixed at 100 feet. This boat is traveling this way, so that means that this side is changing. Why don't we go ahead and call that X? And what we know here is we know dx dt is 150. It's 150 feet per second that is lengthening. And what we want to know, we ask how fast is the angle changing. So our angle there, that's the Greek letter phi. We want here the rate of change of that angle. That's a derivative. We'll call that d phi dt. It's a different way to write that phi. And we want that at the instant when the boat is 200 feet downshore. So this is where you are, so that's saying when x equals 200. So what we need to do is get a trig function in here. So the opposite side is changing, and we know the adjacent side. So in relation to that angle phi, we know tangent of phi is going to be opposite over adjacent, so x over 100. And we want to solve this for phi. Okay, so if tangent phi is x over 100, then that means that phi is the angle whose tangent is x over 100. So phi is going to be inverse tan of x over 100. And that x, that's really a function. That's really an x of t. So it's changing with respect to time. So this is a related rate question is what it is. And what we want now is d phi dt. And inverse tangent, we've actually got a composition of functions here. So inverse tangents are outside function. X over 100 is our inside function. Let me move this derivative down here. So we actually have a f of g of t, because x depends on t. So the inside function is a function of x, but x depends on t, so indirectly it's a g of t. And we want the prime of that. So by the chain rule, that's going to be f prime, plug in g of t, and then times g prime at t. So down here, our d phi dt, whoops, I forgot my prime. We want the derivative of inverse tangent, and remember your inverse tangent derivative here is 1 over 1 plus x squared. So this is going to be 1 over 1 plus, not x squared, but x over 100. And that's going to get squared. So that's our f prime, plug in g of t. Here's our g of t. And then times g prime of t. So the t derivative of x over 100. Well, the 1/100th will come out in front. And then the derivative of x is dx dt. So there's our expression for d phi dt. And we want that at the instant when x is 200. So this will be 1 over 1 plus, so this is at x equal 200 at the instant when the distance is 200. So don't plug that in at the beginning. This will be 200 over 100, and that gets squared, and then times 1/100th, and then our dx dt is 150. So the 100 will cancel in here. That's really 2 squared, which is 4 plus 1, 5. This is 1/5. And then here we can actually cancel 50 top to bottom. So there's 2 50s in here and 3 in here. So that's actually 3 halves. So we've got here, this is 1/5 times 3 halves. That is a 5. There we go. And so this is multiplying straight across 3/10 or 0.3. And that's going to be radians per second. So that's pretty cool. So when you got an angle changing, you can use your derivatives of inverse trig functions to find the rate of change of that angle. And most of the time it'll be tangent is the function that you're using. But it depends on what side you knew. So if you knew this side and was changing, and then this was your adjacent, you'd have adjacent and hypotenuse, so then you'd be using cosine instead of tangent.